Hello, students. Today I'm going to give you basically all the answers to the average atomic mass worksheet. I am going to take my time. I'm going to explain each of these answers. So if you're having trouble with this, skipping ahead and just writing down answers is not going to help you. Make sure you listen to the things that I'm saying. So the first one, it says rubidium is a soft silvery white metal that has two common isotopes. And so the two isotopes that they're giving us are Rb85 and Rb87. It says that the abundance of Rb85 is 72.2%, and the abundance of 87 is 27.8%. What is the average atomic mass of rubidium? So it gives us a lot of information, but there's a little bit that it doesn't give you. If you remember, there is an equation that we use for average atomic mass, or AM, as we sometimes call it, where basically you use the abundance times the specific mass of each isotope to find what you're looking for. So if we get that equation, hopefully it'll pop up here in a second. Hopefully. There we go. And so for this problem, we're going to be dealing with rubidium 85. So I need the abundance of 85 as well as the abundance of 87 and the mass of 85 and the mass of 87. Guys, the mass is what they're giving you. So when they say 85 and 87, they're telling you that the average atomic mass is, in this case, 85 AMU and 87 AMU, respectively. So when we go to fill things in the equation, that's what I'm going to use. So here we go. I'm going to just rewrite this. I know what I'm looking for, average atomic mass. And the abundance of 85, it tells me is 72.2. Now, writing 72.2 is not very useful. As I told you, you really need to rewrite this in decimal form. So we need to write it as 0.722. And instead of 27.8, we're really going to write that as 0.278. So rewrite them in decimal form. That actually makes them useful for when we do this. So abundance then of 85, like I was saying, 0.722 times the mass, which in this case is 85. Yep, 85 AMU. And then we're going to also do the abundance and mass of 87. So abundance is 0.278 times the mass, which is 87 AMU for this problem. And so there you go. So let me get my calculator while OneNote is slowly trying to load all this stuff. And we'll see what we get. So I'm putting 0.2722 in my calculator times 85 plus 0.278 times 87. You guys have calculators. You know how to do that. I'm going to go ahead and call that 85.6. Okay, so we get 85.6 AMU, an answer that should make sense. Because as we saw, the abundance of the isotope 85 is much, much higher. So our final answer should also be a lot closer to 85 than it is 87. And notice I'm putting a box around my final answer. I'm putting units next to my final answer. So make sure you do that as well. All right, the next one's a little more interesting. It says titanium has 5 common isotopes. Good gracious, look at all those isotopes. And so the first thing we're looking for is the average atomic mass. Now, we're going to use the same equation as before, except instead of having just 2 isotopes, we're actually going to have 5 distinct isotopes. So I'm going to have to write kind of small to make sure it all fits on here. But first things first, let's convert all these percentages into decimals. So instead of 8.0, this is going to become 0.08. Instead of 7.8, it's 0.078. That's a nice 8. Let's rewrite that. There we go. It's loading. There we go. Instead of 73.4, we're going to do 0.734, 0.055, 0.053. And if you're having trouble seeing what I'm doing, all I'm really doing is I'm moving the decimal place to the left 2 places. But if you're struggling with this, you can also divide by 100. It'll end up giving you the same answer. So you can divide each of these percentages by 100 to get the decimal, or you can just move the decimal place to the left too. That's all I'm doing. So now that we have all this information, we also have the isotopic atomic masses for each of them. So 46, 47, 48, 49, and 50 are going to be the values. So let's go ahead and make this equation. So I have average atomic mass is equal to, so my first one is going to be for 46, 0.08 times 46 AMU, plus my next one is for 47, 0.078 times 47 AMU, plus 0.734 times 48 AMU, plus 0.055. Hopefully you're seeing this is really just plugging and chugging. This is just putting things where they need to be. I'm being very careful to put units where there need to be units. I'm taking my time and making sure that I put the correct percentages with the correct atomic masses. So just kind of be careful. All right, and here comes the last one. So 0.053 times 50 AMU is what I'm going for there. And that'll load eventually. While that's loading, tell you what, I'm going to put this in my calculator and see what I get. Hopefully it'll load by the time I'm done. And again, I'm just putting this in my calculator. You guys can obviously do this on your own as well. Whenever you're doing calculations, it's usually a good idea to try and check your math twice, because all it takes is one bad keystroke and you've messed up the whole problem. So it's usually a good idea to double check your answer. Now in this case, I'm getting an answer of 47.9 is what I got. So you guys check me at home, but I'm getting 47.9 AMU as my final answer. But yeah, double check me at home, see if I got that right. Okay, and that should make sense. As we can see, our highest isotope by far is isotope titanium-48. So the fact that my answer is 47.9 tells me I probably did it right. Hey, here we go. Which isotope is it closest to? Well, it's closest to titanium-48. Okay, it's definitely closest to that. In fact, if we were to round this to a whole number, it would round up to 48. Is your answer for part A the isotope that's most abundant or least abundant? Definitely most abundant. We saw that abundance was 73.4%. That is definitely the highest abundance. And then it said C, what general conclusion can be drawn about the average atomic mass and the most abundant isotope? Well, okay, your average atomic mass should be closest to the isotope with the highest abundance. I mean, or anything similar to that. But basically, because we're doing a weighted average, we're not just doing an average, because we're doing a weighted average, whichever one has the highest abundance is what's going to have more bearing on your final answer. All right, next one. Number 3, calculate the average atomic mass of gallium, which has 2 isotopes. Well, that's nice. And it says, remember to use the actual isotopic mass for better accuracy. So in the last 2 problems, we were using the rounded mass. So like here, we've got gallium-69 and gallium-71. So in the previous problems, we were using that because that's all the information we had. But in this problem, they're actually giving us the specific, actual mass of each of these isotopes. So we definitely need to use that. So abundance, let's go ahead and round that real quick, just like what we did before. Instead of 60, this is going to be 0.6. Instead of 40, it's going to be 0.4. Again, I'm just converting them to decimals like I've been doing. And now we can do this equation. So the average atomic mass equals 0.6. Now 0.6 is the abundance for the gallium-69. But I'm going to use the more precise value of 68.93 AMU. And then the other one is 0.4, and that is the abundance for the 70.92 AMU value. Let's let OneNote catch up really quick while I calculate this. All right, now I got 69.7. Which, I mean, that kind of makes sense. 0.6 and 0.4, it's not, obviously gallium-69 has a higher abundance, but it's not that different between the two. So the fact that we're close to 70, which is somewhere in between the two isotopes, that should make sense to us. All right, let's look at the next one. Number 4 says use the draw. Sorry, you should be caught up. And again, you can pause because this is a YouTube video. Number 4, use the following drawing to calculate the average atomic mass. Okay, so we are still going to be doing average atomic mass. They've given us some percentages, so we actually need to convert those to decimals first. So let's go ahead and do that. So instead of instead of 0.006, this is going to be 0.00006. Okay, so we add a couple zeros. Again, we're just moving that decimal to the left too. Instead of 0.72, it'll 0.0072. And this one will be 0.9927. Once again, you can divide by 100, or you can just move the decimal place to the left too. It's the same thing I've been doing the whole worksheet. Excuse me. Okay, so now that we have that, that's great. But the next thing that we need is we need the isotopic atomic mass for each of these isotopes, and that's not given. But based on the notes that we took about element boxes, you should know that the atomic mass is really just number of protons plus number of neutrons. Remember, an atomic mass unit is the mass of a proton or the mass of a neutron. So if you add the two together, that gives you the atomic mass of the whole thing. So in simplest terms, all I'm going to go in is add these together. So 92 plus 142 is 234. I probably didn't need a calculator for that. So that's my first isotopic mass. The next one's going to be 92 plus 143, and I get 235. Okay, and then the last one, I'm going to add those up as well, 92 plus 146, and we get 238. All right, and good. OneNote's kind of keeping up with me. Isn't that nice? So guys, now we have all the information that we need. We have the mass and the abundance in decimal form for each of these isotopes. And so now for problem A, we're just going to put all that into an equation. So I'm going to go over here and get things started. So average atomic mass equals, we've got 0.1234 zeros and a 6 times 234. Okay. Plus, the next thing I have, 0.0072 times 235 AMU. And then the last one is 0.99, 27 times 238. So even without doing any math, based on the abundance percentages, you should be able to tell that it's probably going to be 238 or something very close to 238 because the abundance, look at the difference in abundances. And I'm just typing things in, so just be patient with me. And again, I hope that at this point at home, you're trying to type this in the calculator too. So when you guys take your test in a week or so, you're not on your own, like trying to figure this out. You should be able to put this in your calculator and double check me to make sure you're getting the same value. So I get 237.9. So what do you know? That's really close to 238, which should make sense to us. All right, and then I'm going to put a unit on there too. So 237 AMU. Okay, guys, we're almost done. It says it's for honors only, and you know what? I think that you need to do it. So here we go. All right, so for this, we're given some of the information. We're not being given all the information being given. I think that's correct grammar. But luckily, because you know how percentages work, you should be able to fill in everything that you need and figure this out. So guys, percentages, they add up to 100, okay? Typically, percentages are going to add up to 100 or else you've done something wrong. So if our total is 100%, then you ought to be able to do 100 minus 90.51 minus 9.22 and get the missing percentage, which is 0.27. Okay, so 0.27 is that missing relative abundance. And then for mass, now here's the thing. We have to calculate the specific mass, okay, not the general. I know it's going to be close to 22. I know that this is for isotope 22, so it should be close to that, but we're actually going to do the math to figure it out. Now, to understand this, you've got to do just a little bit of algebra. It's really not that bad. So the thing is, we're still going to be using the same equation. Average atomic mass equals, the abundance of isotope 20 times the mass of isotope 20 plus abundance of 21 times the mass of 21 plus the abundance of 22 times the mass of 22. So we're still using the same equation that we've used down the whole sheet. But the difference is we actually know what the average atomic mass is. It tells us it's 20.179 AMU. So what we're actually looking for, our target, if you will, is that we're trying to find the actual mass of 22. So we're looking for this term down here on the end. Now, you could use algebra and just use letters and organize everything around. I think I'm just going to plug in numbers this time to make it a little bit easier. So average atomic mass, 20.179 AMU. Oh, and we need to convert these to decimals again. So even though we have these nice percentages, we really want it in decimal form. So instead of 90.51, we're going to make it 0.9051. This is going to be 0.0027. This is going to be 0.0922. So there you go. It's loading slowly. But anyway, I'm just converting them to decimal form, the exact same thing I've done the entire worksheet. All right, so I'm not reinventing the wheel here. Come on, OneNote. Can you please load the things I told you to load? There we go. All right, so now that we've got all that stuff, let's just plug in some stuff. So abundance of 20 is that 0.9051 value times the mass of 20, which is actually 19.992. Abundance of 21, looks like I'm going to have to zoom out just a little bit because this is going to get kind of long. Abundance of 21 is 0.0027 times the mass, which is actually 20.994. Oops. And I forgot some units. Let's put some units on there. There we go. Finally, we're doing this plus abundance of this last one. Sorry, OneNote. There we go. Which is 0.0922 times, we don't know. We know we're looking for that mass. So that's actually what we're solving for. All right, let me give it a second to catch up to me so you guys can see what I'm going to do. There we go. Thanks, OneNote. Let me center this a little bit better. Scoot over just a bit. There we go. So we're looking for mass of 22. I'm going to go ahead and do some kind of like intermediate work and solve for this in pieces instead of all at once. Oh, my mic fell. That's not good. Stay there, Mike. All right, so I'm going to do 0.9051 times 19.992. And so the reason I'm doing that is now I've solved for this, and I know it's 18.09 AMU, basically. So we're carrying those units. It doesn't really have a lot of physical meaning. So like outside of this problem, 18.09 is not super useful, but the units are still going to transfer. Same for this next term. So for this next section, I'm doing 0.0027 times 20.994, and I get 0.0567. Let's just call it that. And again, this is going to be AMU. And this is all going to be plus that down there on the end. So we're really just carrying that down. Why did I write that? Okay, so we'll just carry that down. And we know that we're looking for that mass of 22 down there in the end. Sorry, guys, I got an email and it distracted me for just a second. So here we go. Let's see what we got now. So using algebra, obviously the best thing that we can do is just start subtracting this stuff over. So I'm going to subtract over 18.09 AMU. That gets rid of that. I'm also going to subtract over 0.0567 AMU and get rid of that. And then we'll see what we got on the next line. Okay, so I'm just doing some algebra, doing a couple of things all on this one step, but I don't think that's too confusing for you guys. Obviously, if you want to get rid of something, you have to do the opposite. Whenever you do to one side, you have to do the other side. You know, basic algebra. So I end up getting 2.0323 is equal to 0.0922 times that isotopic mass that we're looking for, mass of 22. Let me let that load real quick so you can see what I mean. So I just subtracted both of those from that value over on the left side. That's really all I did. Okay, so at this point, instead of multiplying, we need to divide to get rid of that. So my last line, so I'm going to divide by 0.0922, and this has AMU, sorry, I forgot my units. And I'm going to divide the other side by the same thing as well. And my final answer will finally be found. So we've done quite a bit of algebra, but that shouldn't be anything too confusing for you guys. All right, here we go. Final answer. And I'm going to fill it into the chart up here just to have everything complete where it's supposed to be. So let me remind you again, as you guys are doing these problems, show your work like I am. If you are only writing a final answer, you're not going to get full credit. If you are not showing units, you are not going to get full credit. And again, you can type, you can draw on it like I'm doing, or you can submit a picture, but you've got to get that work done. So thank you very much. Thanks for watching this video. Hope you guys have a great day.